Welcome to reaction stoichiometry. This is one of those big words that scares students. That's why I don't like chemistry. But actually, it's very simple. Stoichiometry only means is amounts. Okay, we're going to be dealing with amounts. If you have two molecules A and B that react to form C, if I have so many grams of A, how much C do I get? If I have 2 grams of A and 2 grams of B, do I have any leftover? That's what we're talking about, okay? So don't let the name scare you. Now, a balanced equation gives you a lot of information because the chemical formulas tell you who are the reactants, who are the products, the coefficients give you the relative number of atoms or number of moles, and the relationship between all these amounts, that's what we call the stoichiometry. I like to compare this to cooking, okay? And we see several examples. But for instance, you have a recipe that to make 8 pancakes, you use 1 cup of pancake mix, 3/4 of a cup of milk, and 1 egg. You could write the recipe as if it was an equation. 1 cup of milk plus 3/4 of a cup of mix plus 3/4 of a cup of milk plus 1 egg gives 8 pancakes. Actually, I used to run my recipes like that. If it had to be cooked, like if it was going to be baked in the oven at certain temperature for so long, where do we put the extra information? Always on top of the iron. I don't do anymore because my husband does most of the cooking now, and he likes it spelled out. But I used to write recipes like that. But now imagine that instead of 8 pancakes, you want to make 24 pancakes. Well, you know that 8 pancakes require 1 egg. You're going to be doing just like the way we learned to do in chemistry, because pancakes, first, where do I get 1 egg? 8 pancakes from the recipe, right? 1 egg, 8 pancakes. So now pancakes cancel out and it says, I need 3 eggs. Yeah, you say, I could have done that on my head. Yeah, I agree. But when we move from cooking to chemistry, you're going to be dealing with grams because that's what you measure in the lab. They're going to be asking you for grams, but the reactions are going to be taking place between moles. So it pays to do the calculations this way because it avoids a lot of confusion. It avoids you from making silly mistakes. Okay? This is just a very simple analogy to explain to you the advantages of stoichiometry, which it allows you to do. So a balanced equation can be used like a recipe. And from the balanced chemical equation, we can determine how much of a reactant you need to react with a given amount of another one. I have 2 grams of A, how much speed do I need? You can calculate it. Or I want to get so many grams of C. Well, how much A and how much B do I need to get that? Okay. Now the coefficients is what determines everything. This book calls stoichiometric factors. I like mole ratios better because it tells you what it is. It compares the number of moles in one to the other. And I know the PowerPoint keeps calling stoichiometric factors. I will keep reminding you, we're talking about mole ratios. I'm going to keep saying it over and over and over because this is the only thing that can go wrong with this type of problems if you don't work with moles. If you work with grams, it's not going to work. Got to a point years ago, I didn't know how to get my classes to everybody convert the grams to moles. And I think I told you before, but this was actually the first time I did it. I made a little cheerleader ditty about changing to moles, and I went, when they were taking an exam from room to room, because it was kind of mixed with other chemistry students, they have a common exam, and I went dressed as a cheerleader, dancing, changing to moles, changing to moles, changing to moles, go to another room, changing to moles, changing to moles, because it's so important. Okay, that's why I prefer to use the term mole ratio, because it's another indirect way of reminding you, changing to moles. Don't forget moles. In fact, I tell the students, when you get this exam, if I was you on top of the exam, write real big, change it to moles so you don't forget. So you have this equation. Nitrogen reacts with hydrogen to form ammonia. This shows you that the ratio of hydrogen to ammonia, or ammonia to hydrogen, is 2 to 3. So this can mean 2 molecules, or 2 and 3 dozen molecules, or moles. Most likely, we're going to be dealing with moles. But it's the same ratio, 2 to 3, 2 to 3. Okay? It never means grams, because you know ammonia and hydrogen weigh different. So 2 moles of ammonia don't weigh the same thing that 2 moles of hydrogen. You know that. So it never means, I just want to make sure, never 2 grams of ammonia, 2 grams of hydrogen. Never. Out of the question. There was one semester I was so upset that I said, if you write grams instead of moles, not only you're going to lose the credit because you didn't get it right, but I'm going to take extra credit off because I've told you so many times, never use gram ratios. I didn't do it, okay? But I did say. So basically this is very simple because I've given you moles. You have this equation. If you have so many moles of aluminum, how many moles of iodine do you need? And you say, okay, moles of aluminum, you use the mole ratio, and you say 3 moles of iodine to 2 moles, 3 moles of iodine to 2 moles of aluminum. Why do I put the 3 on top? Because I weigh moles of aluminum, cancels out, and it gives me moles of iodine. That's what I want to. Remember, we talked about that before. If you put the ratio backwards, then the moles of aluminum will not cancel out, and you know you did it wrong, and you can repeat it again. You wasted maybe 10, 15 seconds. Don't forget, your units are right because they are cancelled out. 3 significant figures, 3 significant figures. These are exact numbers because they're talking about moles, the number, the counting moles, okay? So 3 significant figures in here, 3 significant figures in there. Most of the time, though, they're not going to give you moles because, once again, in the lab, when you want to get a certain compound, you're going to weigh and scale. You're going to have grams. And they're usually going to ask you how many grams. Okay? So what mass of sodium hydroxide is necessary to produce 16 grams of milk of magnesia? That's magnesium hydroxide, and that's a very common antacid. Okay? So they give you the equation. Magnesium chloride, sodium hydroxide react to form the milk of magnesia, solid, plus sodium chloride. Now the problem is they're giving you grams. Now, watch out. When they ask you for mass, they're not telling you what unit. So I always tell the students, if you give me that in kilograms or in milligrams or centigrams, I have to accept it because the question is not very specific. But the first number you're going to come up with is grams. Why would you change it? Okay? But because I'm asking you for mass, if you answer moles, you're only partially right. You didn't finish. Moles is number of atoms. Mass is grams. So don't stop at moles, please. So we begin with the magnesium hydroxide and we change it to moles. How? You look up the molar mass. Usually in an exam, I do give the molar masses to the students. I'm assuming your staff will do that. But this is the molar mass, so 1 mole magnesium hydroxide weighs this one. So now grams and grams cancel out. That tells me how many moles of magnesium hydroxide. Okay? It's asking how much sodium hydroxide do I need. Okay, to get 1 magnesium hydroxide, I need 2 sodium hydroxides from the equation. So 2 moles sodium hydroxide, 1 mole magnesium. I put magnesium hydroxide at the bottom, so when moles and moles cancel out. So that tells me how many moles of sodium hydroxide. But if you stop here, you're not finished because they want mass. So probably will be given, you can calculate also easily, 1 mole of sodium hydroxide weighs 40 grams. So now we change moles, and you do these calculations. You know that the last thing that you got left was grams of sodium hydroxide. All of these are either from their exact numbers, either because by definition, or these are counting numbers, so you have two significant figures. My answer has two significant figures. Do you have to do like a long equation like this? Not really. I mean, you could change grams to moles, then do the mole ratio, separate, and then change moles to grams and have three different equations. The advantage of doing it this way is that when you're finished and you go over, you can go and say, okay, so I changed grams that cancel in here. I got moles that cancel in here, moles in hydroxide. So you can check it very quickly, very easily. And you notice that you did cancel everything out, and all you have left is grams of sodium hydroxide. So you did it right. It's just easier, I think. But if you choose to do it as three separate, that's your business, okay? I really think it's worth getting used to doing this way, long term. So this flowchart is trying to show you if you have a liquid, how do you know moles? Well, usually with a liquid, you use the density to calculate the mass. Remember, density is the mass divided by the volume. So if you know the density and the volume, you can calculate the grams, and then you change it to moles. You have a solution. We've already talked about solutions. Molarity is moles divided by the volume, so you can calculate the number of moles. I don't know who would give you a number of particles. Instead, let me replace it with something else. If you're dealing with a gas, you're going to be dealing with pressure, volume, temperature. We'll see that in another chapter, but from this information, you can calculate the number of moles. Then, that's the mole ratio. Use the mole ratio, and you can use it to determine how much of another reactant or how much product. It may be product, and you go back to reactant. Anything that's in the equation, there's a mole ratio between any two of them. It's not only to compare the two reactants or the reactant to a product. You can compare anything you want to, one product to another product, whatever. Then keep in mind, most likely they're going to ask you if the product is a liquid. They'll probably ask you for the volume. Well, you have moles. You change it to mass, and using the density, you can change to volume. If it's a concentration, if you have moles, and you know the concentration, you can determine the volume. Once again, this is silly, but if you have a gas, if you have the number of moles, you can determine either the pressure or the volume or the temperature for the gas. The key is that you get whatever they give you, you change it to moles. And then read the question. Are they asking me for the answer in moles, or do they want grams, or do they want liters, or do they want, and give the answer in the units that the question is asking. But if you forget to change whatever they give you, that's why I put it, whatever they give you, if you don't change it to moles, the whole problem is going to be wrong. Once again, there's always one thing that say, if you only learn this out of the chapter, that will help you tremendously. Change it to moles. That is actually, that's my motto for college chemistry 1. Change to moles. Change to moles. Now, we are also going to be looking at the reaction yield. You want to know how much product you get, okay? In the example we've been given, they call it stoichiometric amounts, meaning they give you exactly the amount that you need to react. There's not too much, not too little, anything like that. But that's not realistic. That's not what happens in real life, okay? So imagine you're going to make grilled cheese sandwiches, and I told you I like cooking as an example. So to make a grilled cheese sandwich, you use 1 slice of cheese, 2 slices of bread, and that makes 1 sandwich. So you look in your kitchen, and you have 28 slices of bread, 11 slices of cheese. How many sandwiches can you make? You can only make 11, right? Because once you have used all of the cheese, are you going to give someone 2 slices of bread with no cheese in between them? That would be a toast, but not be a grilled cheese sandwich, right? Once you run out of cheese, you cannot make any more grilled cheese sandwiches. Okay? So you use all of the cheese, but there is 6 slices of bread left over. Same thing with chemistry. You're going to have too much of something, not enough of another one. But the number of sandwiches is limited by the number of cheese. Correct? Because when you use up all of the cheese, that's the end of the story. That's what we call the limiting reactant if you use chemistry. The one that determines how much product you get, that's the limiting reactant. It's always entirely consumed. That's why you cannot make any more. The bread, you have more bread than you need. So we call that the excess reactant. A very common mistake is assume that the limiting reactant is the one you have the least of. Not necessarily. Not always. Because it depends on the mole ratio. And we're going to see examples. So don't you ever, when they ask you who's the limiting reactant, look at the number of. And some people look at the grams and say the one that had the least. Some people go as far as changing to moles, and the one you have the least. No, no, no. Which one gets used up completely? Which one makes the least amount of product? That is the limiting reactant. Okay? So this is a real chemical equation that you have 3 moles of hydrogen, 2 moles of chlorine, but you know the ratio is 1 to 2 to make the product. So 3 moles of hydrogen can make 6 moles of hydrogen chloride. 2 moles of chlorine could, all of this is in theory, could make 4 moles. What do you make, 4 or 6? You make 4. Why? Because once you make the 4 moles of hydrochloric acid, you're out of chlorine. It doesn't matter how much hydrogen there is. If you run out of chlorine, you're done. You cannot produce any more hydrochloric acid. When the chlorine is consumed, you cannot make any more hydrochloric acid. So chlorine is the limiting reactant. Yes, it just happens that there is less chlorine than hydrogen. That's just a coincidence, okay? That's not the definition of limiting reactant. It just happened to be the one you have listed. Okay, fine. It's completely irrelevant. It is a limiting reactant because it produces the least amount. So this is what I'm trying to explain here. The reactant yielding the lesser amount of product, that's the limiting reactant. And you're going to find examples where there is more of the limiting reactant than of the other. But because you use it all up, because it produces less product, and we're talking in theory, if all of this reactant was used, how much would you produce? If all of this one was produced, the one that produces the least, that's the limiting reactant, because that's the one that's going to get used up, regardless of the actual amount. The other substance is the excess reactant. So we're saying here, this was the limiting reactant. That means that the other one is going to be the excess reactant. And be very, very careful. This definition is extremely important because it doesn't matter how many times I explain it. The day of the exam comes, I give an equation. The first question, which one is the limiting reactant? Half of the class automatically puts the one with the least amount. I'm going to tell you a secret. I always choose an example for the exam where the limiting reactant is in larger amount than the excess reactant. So those students who didn't listen to me automatically get that question wrong. No, that's not mean. That's just making sure they listen. If it happened to be that the limiting reactant there was less, they could answer the question right and still not know. So I word the question in such a way that if they don't know it, they cannot get it right. Please, this definition is critical in stoichiometry. This is just showing you again for the reaction. After the reaction, you have the chlorine in green, the hydrogen. You use up all of the chlorine, right? There's no chlorine that hasn't formed hydrochloric acid. So chlorine is the limiting reactant. It's all used up. There's hydrogen left over. Why? Because it's excess. Very simple. Now, if you calculate on paper the amount of product that can be produced by a reaction, and you have to base it on the limiting reactant. Because again, remember, when you use up all of the limiting reactant, you cannot make any more product. But you determine who's the limiting reactant, you calculate how much product you get. That is the theoretical yield. That's on paper, in theory. The problem is in the lab, things don't always work out like that. So the amount that you actually obtain is the actual yield. And it's often less because there's all sorts of problems. Sometimes you have complete side reactions. Okay? One of the things that we do in the lab is to burn magnesium to produce magnesium oxide. Magnesium oxide. But the problem is in the air, there's also nitrogen. So you actually get a mix of magnesium oxide and magnesium nitride. So you don't get all the magnesium oxide that you could from this amount of magnesium because some is going to be used up in a side reaction. And that's very common. Your reaction may be incomplete. It didn't react completely. One of my favorite labs was looking at the calories in a Dorito. So we'll burn a Dorito and use the flame to heat up some water, and by looking at how much the temperature of the water went up, we could determine how many calories the Dorito had. When we burned the Dorito completely, the number came out very, very close to what it said on the bag of Doritos. But many times the Dorito didn't burn completely. There'll be a little bit left over. So sometimes reactions don't go to completion. It's an experimental problem. Sometimes the product is difficult to recover. If it's difficult to recover, you may not get all of it. So your actual yield is usually less. But let me warn you, it's never more. Have you ever got 120 in an exam? No. Because if you answer all of the questions, you get 100. If you miss questions, you get less than 100, but you don't get more. Okay? So people who tell me an actual yield that is higher than the theoretical yield, just feel like saying, look back again, you made a mistake. Okay? Maybe if it's in the lab, you didn't let the product dry enough, so there was some words changing. Maybe you made a mistake someplace. Maybe calculating the theoretical yield, you made a mistake, and that's why the number does not come out right. But something is wrong. You cannot get more than the maximum that you can possibly get. Another way to express the yield is percent yield. You divide the actual yield by the theoretical yield and multiply times 100. Now we said the actual yield is always less than the theoretical yield. So your percent yield is always going to be less than 100%. Well, let me call it less or equal. I don't know if in the lab you could actually get 100% yield, but definitely you cannot get more. When we do a chemical reaction in the lab, I'm always expecting the students to give me the percent yield. So I have someone very happy turning in. I'll never forget. Someone actually reported she had got a 285% yield. We was isolated vanillin, okay, the extra that I used to make chocolate chip cookies. And she was looking at the weight of the initial reactant, and she made the calculations, weighed whatever she had, and like I said, she had a 285% yield. I told her, you know what? You need to drop out of school. She looked at me like, drop out of school? I said, yeah, because if you can play a little bit with this chemical and you get an extra 185% vanillin that has appeared out of nowhere, look at the price of vanillin. You could make a business. It's like if you were supposed to get 100 grams of vanillin, you get 285. You can get that extra 185, that's free, that has come out of the blue. It's all profit. If I was you, I'd drop out of school and open a vanillin factory because your profit is going to be outstanding. And she finally understood. It's impossible. You can get more than 100%. Okay? if you come up with a number that's more than 100, probably the most likely thing is that you put the theoretical on top and the actual at the bottom, reverse them, and everything is fine. And make sure you use the same units. You don't want to have one in grams and one in milligrams, because then the units won't cancel out, and that's also going to affect your number. So for instance, you're making these grams of copper sulfate react with zinc metal according to this equation. So they want to know what is the percent yield. Okay. And they're telling you, or they tell you they have excess zinc, and this is how much product you get. So this is your actual yield. But we need to know the theoretical yield. So we get the grams of copper sulfate, we change them to moles. Remember? Use the molar mass. So now we have moles of copper sulfate. What is the mole ratio between copper and copper sulfate? It's a 1-to-1 ratio. I still write it down, okay, even if it's a 1-to-1 ratio, because you get in the habit to always do everything. If you start skipping steps because you think that's unnecessary, you're more likely to make a mistake. And that way you can get to see moles of copper sulfate, cancel it out. So I have moles of copper. How much does a mole of copper weigh? So I change it to grams. This is my theoretical yield. So now I have the actual yield and the theoretical yield. I divide the actual by the theoretical, 77.3, which is actually very good yield for chemistry. Okay? But once again, you realize if you reverse the order, it's going to be more than 100. That should be a red flag telling you, you made a mistake, go back. Never give more than 100% yield. This is really not difficult at all, okay? Like I said, can compare to cooking. It's very, very simple, but like so many other things, it takes practice. How do you always remember to change into moles? How do you practice, practice, practice? Surprise, I have a worksheet where you can do plenty of practice. Sometimes you're going to, one of the reactants, the one that you have the least is going to be a limiting reactant. Sometimes the limiting reactant is going to have more to begin with. I try to make a big variety of problems and ask you different questions, but in general it's going to be, if you have so many grams of this and this, how many grams do you have? We're going to be looking at, okay, if you have an excess reactant, how much excess is left? Hey, we didn't discuss that. But let's say that you need 2 moles of, remember we're talking about, you have A and B producing C. And you need 2 moles of B, you have, I don't know, you spend 3 moles of B. So how much is going to be left over? It's very easy. 3 minus 2, there's going to be 1 mole excess. You may not know how many moles, but from the grams of A, calculate moles of A, then you know how much B you need to, and whatever you have minus whatever you need, that's going to give you the excess. Again, there will be problems like that in that worksheet. So this is a worksheet that I very, very strongly recommend, and you can get it by going to the video description, go to Wisant, and sign up for a tutoring session.